Alright guys, here we are back in chapter 14 with an example about a damped oscillator. And the system that we have here is a pendulum. It weighs 500 grams. The length of the string is 30 centimeters. And we're given a fact here. It says the pendulum's energy decays to 50% of its initial value in 30 seconds. And they ask us some questions here. A, what is the time constant of the decay? B, what is the value of the damping constant, which is the symbol B? And what is the frequency of oscillation for this damped system? Okay, so if we're going to approach this problem, the first thing we need to do is recall the kinematic equation for a damped oscillator, and that is that the position x is given by a times e to the minus bt divided by 2m times the cosine of omega t plus the initial phase phi 0. And this exponential piece here, this gives us the maximum displacement x max at a time t. Now the fact we're given is that the energy is decreased by 50% in 30 seconds, so we need to come up with an expression for the energy, and we'll recall that the energy for an oscillator is 1/2 k times the amplitude squared, and in this case our amplitude decreases in time, so we're going to replace this a with x max, and we get that the energy as a function of time is equal to 1/2 times k. Okay, we're going to get an a squared here, and we're going to get an e to the minus bt over m. Okay, e to the minus bt over 2m squared means we get a factor of 2 up top, and so we lose the factor of 2 in the bottom. So the fact that we're given says that the energy at 30 seconds, which I'm going to call t1, is equal to 1/2 the energy at time equals 0. So plugging that into this expression here on the left-hand side, you get 1/2 times k times a squared times e to the minus b times t1 divided by m is equal to 1/2 times k times a squared times e to the minus b times 0 over m. So this piece goes to 1. E to the 0 is 1. The a squareds cancel. Oh, I lost a factor of 1/2 here, so this is going to be 1/2 times all this. So I'm going to change this to a 1/4 because of this 1/2 here, and we have a 1/2 in the expression, so this becomes a 1/4. The k's cancel, one of the 1/2s cancel, and we end up with e to the minus bt1 over m is equal to 1/2. All right, well, we're interested in knowing the time constant, so let's rewrite this in terms of the time constant. This is going to be e to the minus t1 over tau. Remember that the time constant is equal to m divided by b as units of seconds. That's going to be equal to 1/2. Taking the natural log of both sides, on this side we're going to get minus t1 over tau is equal to the natural log of 1/2, which is equal to the natural log of 1 minus the natural log of 2. Okay, natural log of 1 is 0, e to the 0 is 1. So we end up with minus t1 over tau is equal to minus the natural log of 2. Minus signs cancel, and we end up with tau is equal to t1 divided by the natural log of 2, which is equal to 30 seconds divided by the natural log of 2, which is equal to 43.2 seconds is our value for t1, or for tau. So this makes sense. It says the energy is decreased by half in 30 seconds. Tau tells us the amount of time that it takes for the energy to be decreased to 37%. It's 43.2 seconds, which is slightly longer than the 30-second fact that we were given, so that makes sense. All right, part B asks what is the value of the damping constant? Now we need to find the damping coefficient B, which is pretty straightforward. We know that the time constant is equal to the mass divided by the damping constant. We already know the time constant, so we need to solve this for B. We get B times tau is equal to m, or B is equal to m divided by tau. So B is going to be equal to 0.5 kilograms divided by our 43.2 seconds. Plugging that into our calculator, we get a value for the damping constant of 0.115 kilograms per second. Part C asks us to find the frequency, omega, of oscillation for this damped system. Now, if the system was undamped for a pendulum, omega would be equal to the square root of g over L. We'll call this omega 0. And for a damped oscillator, we have that omega is equal to the square root of omega 0 squared minus our damping constant b squared divided by 4m squared. And I'm going to go ahead and use this relationship that tau is equal to m over b. So we can rewrite this one more time as the square root of omega 0 squared minus 1 over 4 tau squared. Just apply the substitution. Tau is equal to m over b. The frequency is what's asked for here, not actually the angular frequency omega, so that's going to be 1 over 2 pi times omega, which is going to be 1 over 2 pi times the square root. Omega naught is g over L. Omega naught squared is g over L. Omega naught is the square root of g over L. Minus 1 over 4 tau squared. Plugging in some numbers, we get that the frequency is 1 over 2 pi times the square root of 9.8 meters per second squared divided by 0.3 meters minus 1 over 4 times tau, which is 43.2 seconds. So we end up with the frequency being equal to 0.91 hertz.